getting recorded. That's the homework 4, due Monday. Second one.
We decided sometime in the class for that.
I was just going to write it so that from my perspective that's what it is, unless you guys tell me. So,
Yeah, we talk about that, and then after for the evening time, I think you have the
Yeah, it doesn't work with my schedule, unfortunately.
yeah. That's why we decided it for the class time.
okay. Yeah. Anything else anyone wants to comment on? Okay. We defined what a complex number is last time. Usually, it's very convenient to define a derivative in any of a function, and now we have a new function which is dependent on two variables in a sense, x and y, on a complex plane, and we would like to define a derivative on that, and this will be a special derivative in the sense that its value is decided by any direction you come from. So the moment you think of a derivative, first thing you talk about is a function of x, right? So usually the way we did first time learn derivative is a function of a single variable x, but if you think of temperature in this room, it depends on three quantities, x, y, and z, right? Then you have a derivative with respect to x, derivative with respect to y, derivative with respect to z. So think of a temperature in this room is x, y, and z. We can capture all those things in a vector form, and that is done by the gradient of the temperature in this room will be equal to the derivative or the change in the temperature in the x direction plus the change in the temperature in the y direction plus a hat times change in the temperature in the z direction. In general, if I were to multiply this with a vector A, so this is one of the first derivatives you learn in vector calculus. Here you might see it in electrodynamics. This is a directional derivative. So this is basically ax and d by dx plus ay by y plus az. Whatever that structure is, intuition is that this is the derivative. This is a directional derivative. In the direction of derivative in the direction of A, right? Maybe that's the better way. Derivative in the direction of A. Pick a direction, let us say towards east, and you see how the temperature changes in that direction. Just the very definition means that in different directions you can have different derivatives. We will be working in 2 dimensions, which is a complex plane, or it has a lot of similarities with a 2-dimensional plane. And the nice thing about the derivative we are going to define today is that it doesn't depend on the direction. It doesn't matter in what direction you come from, all the derivatives will have to be the same. And that puts in a lot of constraint on the kind of functions we talk about. And that is what will be called an analytic function. And that's what we are going to, and the properties of that is going to involve us for the next 2 weeks or 3 weeks. So this is the idea of analytic function. Z is equal to x plus iy is a complex number, and you can think of it as a complex plane. So there is an x, there is a y. Often you denote this as, this means this is a complex plane. X is called the real part of the complex number z, y is called the imaginary part of the complex number z, and in general a complex number will be z here like this. The I that shows up here is a special number. It is square root of -1. This is not really to be thought of as two coordinates. It's not x comma y. It's a linear combination of x and y. Okay, so that's important. Remember, if you have take a generic variable, so if you have ax plus by, right, and if you have a function of t, f of t, which is equal to function of a of x plus b of y, the derivative of this function f with respect to x over derivative of the function with respect to y would be equal to, this is two derivatives,
Partial y with respect to x. Basically, we're-
partial y with respect to x, no?
No, okay.
That will be 0, right? Because x and y are independent.
This guy says the Jacobian.
Say that again?
It looks like the Jacobian.
Jacobian, remind me what Jacobian is. And I know what you mean, but I think
Partial
still.
one coordinate system over partial a different coordinate system.
Ah. Yes, that's going too far. Yeah, probably, yeah. Maybe there is a connection. I don't want to say it is wrong, yeah. Maybe that is what it is, but let's do an actual derivative, right? I mean, since no one is giving an answer, let's say cosine of ax, let's say 2x, right? If we don't even put an a there, 2x plus put a prime number, so that the cancellations may not be easy. So this is f, let's say. What is cosine of, the derivative with respect to f? That you should be able to do it. Tell me.
Minus sine of 2x plus 7y times 2.
Times 2, right? You
7 or negative 7 sine.
why is it negative? Oh, because it is, yeah, negative, yeah, thank you. Sine of 2x plus 7y.
Yeah.
What's the ratio?
2/7.
2/7, right? If you divide this out, it's 2 over 7. So what might this be?
A by 2, A by B.
Right? So it should be a by b. And why is that? How did you get sine of 2x plus 2y? It is whatever is the argument, you first fix that. So you would say if this was t, so if you were to do this, you would say this is partial derivative of the argument, and this is a chain rule, right? dt by dx. And that's why I think maybe what you are saying might have something, but I'm not seeing through it. This is d by dt and dt over dy. Whatever this is, the argument wise that will always cancel out, and it is the derivative of the argument that eventually comes out in this case. Right? So this is a over b. I emphasize that because this is a structure like this. If I have a complex function I'm going to define, its derivative with respect to x is going to be related to the derivative with respect to y because it's a linear combination of them. You in electrodynamics and many places in physics, because everything is local, you always have functions of the kind position 1, this is the position of the source, let's say. This is the position of the source and position of the observer. Right? Usually there is a detector, there is a source, and most of the physics depends on the distance between them. Right? And let's make it simple, let's make it one-dimensional. Right? What is its derivative with respect to Rs? And suppose I say this is alpha times derivative of f with respect to R naught. So if I move the detector versus move the source a little bit, so that's how does the result, experimental result, change because I changed my source a little bit versus I changed my observer a little bit. How will this depend on what is alpha? A over B. Right, and what is that?
-1.
-1, right? So alpha is just -1. Right, 1 over, like, take the charge or gravity, the potential is where the charge sits, RQ, minus where the observer is, right? So it doesn't matter whether it is the observer or the source, or whatever you move, relatively that will be the same idea, but I want to emphasize that because that shows up here, because we are talking about functions of that kind. A complex function will be defined as f of z, so we just call f is equal to f of z, where z is x plus iy. This is very much like a and b. Here a is equal to 1, b is equal to I, which is a imaginary number, which is square root of -1. Nevertheless, it's a number, right? So we will that will play an important role in physics. This shows up in the form of Laplacian. Whenever whatever satisfies a Laplacian, that has to satisfy some conditions. So we will see that again in the end of the lecture. Okay, so that all that is just observations. We want to define a derivative. So we will pretend that we know how to take derivatives in one direction, not just pretend we know, right? We have learned what derivative in one dimension is. So let's remind ourselves one-dimensional derivative, right? One-dimensional derivative. And now I have a function f, which is a function of a single variable. X is real. Okay, and here we will pretend that there are nice function. It doesn't suddenly go to infinity and so on. So that's what usually we call it well-behaved function. There are more details that should go in there, but we are pretending that we are not going for extreme situations. So all the functions we talk about will be real. How do you define a derivative?
You take some point away from x, so let's say f of x plus a minus the original point,
And
over the distance, and you take the limit as the distance goes to 0.
right. So f of x, you make a small change in x, that might be delta x, and you look for what is the change in the function, and then you take the ratio of, this is basically difference in that, but it is the distance itself, the x cancels out, right? First you say the change could be anything, but then you're interested in really tiny changes, infinitely tiny changes. So you want to take the limit delta x tends to 0, right? So that's the definition of the derivative. And we will also, so when I say one-dimensional derivative, we will, even though first time originally when you're doing it, whether the derivative comes first or the Taylor expansion comes first, that's always a question. Here, since we want to go into the analytic function quickly, we will say the Taylor expansion in one dimension is known, right? So I'm going to emphasize this using the idea of Taylor expansion. So what is Taylor expansion?
Expanded with the function in terms of the powers of its derivative.
Correct, right. So let's say f of x. Yeah, f of x can be, let's write it as f of x plus a, right? Is equal to f of x itself plus a over 1 factorial times the derivative of the function at x equal to, oh, this is just x, right? So this is just x. You can write it in different forms. This is a square over 2 factorial second derivative of f with respect to x squared and so on. And these are all dependent on x. Sometimes you also write this as f of x around a point a will be f of a plus x minus a over 1 factorial, and then derivative of f with respect to x at x equal to a plus x minus a the whole square over 2 factorial this is probably more popular, but substitute x with x plus a, then f of a becomes, you're setting x equal to 0, so around x equal to a, this is how it will look like. I think I might be not saying it correct, but this is just a translation of that. Any questions on that? If I were to pretend that this is known, it makes it easy to take this derivative. So I take the right hand side of this quantity, so limit delta x tends to 0 of f of x plus delta x minus of f of x divided by denominator is just delta x. That's equal to 1 over delta x, and expanding this out, this is f of x plus a is now delta x times the derivative, and there are higher terms which I'm not going to neglect. Notice the argument now, this is minus of f of x. The first term cancels out. If this were not to cancel out, if f of x doesn't cancel this f of x, 1 over delta x will be infinity, right? 1 over 0 comes up. So once this has cancelled out, the next term comes into power, and that delta x cancels out that delta x very cleanly, and this is what is remaining. There is a third term, but that doesn't contribute because there is a higher power of delta x in the limit that will go to 0. So it's not an approximation, this is exact in that limit. Is that argument clear? So maybe I should emphasize that this is delta x squared over 2f factorial, and there is second derivative there. So this is plus delta x squared over 2 factorial and minus f of x. Notice this looks like a structure of 0 over 0, but how are we making it work? The 0 in the numerator, we make sure it cancels out. If it has to cancel out, the first term has to go away. So first term has to cancel that, so that's always cancels out because we are subtracting that term out. This cancels out, so the infinity is no more there. Then you might argue, what about the second term? Second term never becomes infinity because this is a higher power in delta x than the denominator. So all the other powers go to 0 exactly. In the limit, they all go to 0 and only this survives. Right? So that's that whole structure, or that cancellations are important. Right? There's a 0 in top, there's a 0 in the denominator, and that cancellation is important. And this whole analysis of zeros and infinities, like whenever something is in the denominator, it goes to infinity. Whenever something is in the numerator, it goes to 0. That combination plays an important role in the analysis of analytic function. The denominator going to 0 will be called a pole, numerator going to 0 will be called a 0, and the interplay of this decides how these functions will behave. So that's one dimension. Now we want to extend this to 2 dimensions, correct? So we have f of z. This is now equal to f of x plus iy. But whatever function we deal with here, if it is rational functions and elementary function, we can always play or distribute things around, and this can always be written as now not necessarily as x plus iy. This is x comma y. Remember the difference between when I write it as plus and comma. Comma means there are 2 variables, 2 independent variables. This one has constraint dependence in there. Plus I times v of xy. Now there are 2 parameters in these functions, u and v. And any function can be written as primarily because all additions or subtractions are involved, all the operations can be distributed into plus and minus. And now we want to define the same idea. We have x plus iy. So this is a plane, x comma y, and at this point x comma y, I have a value of the function. I want to shift it, and you would say there are many ways of shifting it, right? So this is x plus delta x and y plus delta y. Depending on my delta x and delta y, I can shift it in this direction, I can shift it in this direction. There are infinite ways of shifting x and y. Right? If I want to take a derivative here, in this case also there were 2 ways, right? I could have gone to the plus side or to the minus side. Right? There were 2 ways in that sense. Here we are going either to the or in all directions. In any, if you think of it as vector, you're actually talking about any direction on a plane, and accordingly this function will change, and we want to find the change in them. So we will do pretty much the same as what we have there. So let's define our derivative, the f by dz, as limit delta z going to 0, where delta z, so I'll write it in the denominator here, right? And this is f of z plus delta z minus of f of z divided by z plus delta z minus of z. What is delta z? Is equal to a small change delta x plus I times delta y. A small difference. I mean, it is intuitively very clear what I mean. Do this again, explicitly do this in terms of u and v. And now I say that delta z going to 0 means I have to go take delta x go to 0, delta y go to 0. There are two variables. So delta x going to 0, delta y going to 0. And now f of z plus delta z will be u of x plus delta x, y plus delta y. And then there is two terms in that, I times v x plus delta x and y plus delta y. Subtract out minus u of x comma y minus I times v of x comma y. Write this out and you have z cancels out, delta z is delta x plus I times delta y. Again, this is not a unique way of doing it. There are many ways of coming towards the point. We are at this point keeping it all free. It can be. In this spirit, we know that what should be done. I know how to Taylor expand a function u. This is just a function that depends on two real variables. Right? If I know how to do it for one variable, I know how to do it for two variables. First do it in one variable and then each term do it in the second variable, right? So it's a double summation if you want. It's only the leading power that contributes, so I'll expand it only to this, right? The second one anyway, the same argument is going to go through, that in the extreme limit in the denominator that won't survive. Right? So we have to worry about only till the first term. But it should be understood that the same arguments will go through for that also. So let's see how this comes about. So this is limit delta x going to 0, delta y going to 0. Expand this out now. When I expand the first term, I have to go in the delta x and in the delta y. There will be two terms, right? So we write that down. So this is u of x comma y. That's the first term. When I expand this, I have delta x and then the partial derivative of u with respect to x. The next one, there is a y also. There is a partial derivative of u with respect to y. That's the expansion of this. There will be higher terms here, exactly like here. There will be order delta x or delta y. At least one of them will be higher in power. Right? At least delta x would be there, at least delta y would be there, plus higher terms. Okay. This also can be expanded, plus I times v x comma y plus I times delta x, partial derivative of v now, with respect to x, plus I, partial derivative of v with respect to y, and subtract out everything, or first I have to show more terms, right? Plus I higher terms and minus of u of x comma y minus I of v x comma y. Is this going in the recording? I think this line is somewhere where it cuts, but I think all of you guys are here that much. It'll be fine. With me? Yeah. That expansion? Almost there. Purposely going slow so that it's clear. This should be very crystal clear what we did. This is sort of the definition of analytic function. Exactly like here, if I want to avoid the singularity or the denominator going to 0 without the numerator compensating for it, this has to cancel out, right? And that really cancels out. The Taylor expansion allows that to happen, and the same thing in here. Right. Whatever is remaining is equal to limit delta x going to 0 and delta y going to 0. And how should I collect this? Yeah, let's collect delta x together. There are two terms with delta x. This term and collect this, so plus I times dv by dx, and that is a delta y. I want to write that term first, so that is I delta y dv by dx or dv by dy. That's this term here. Plus, so that's going to be minus I, right? Minus I times I is plus 1. And divided by delta x plus I delta y. And if you notice, this is not really working the way this should have worked, right? Here it was very nice. Delta x cancelled out. That delta x cancelling is very crucial because that's a 0, this is a 0. 0 over 0, if they are of the same power, they can cancel out and then we can have a unambiguous answer. But here that's not cancelling. Delta x, the denominator, does not cancel the numerator, anything in the numerator, right? So in a sense, in this approach, derivative is not very well defined at this point. We are sort of stuck at this point. But that is, we can save it if we put additional conditions. We really wanted to cancel it, so we look for under what conditions will that derivative be well defined. Right? So otherwise, derivative is not well defined on a complex plane. But there are, under very special conditions, there can be a cancellation, and that is when this quantities in the parenthesis, if they are the same, then they can factor out. Only if they are the same. Right? So if, right? So this is limit delta x tends to 0, delta y tends to 0. This is equal to delta x plus I delta y times, if they are the same, so how do I write that? Yes, I'll just write one of them, right? If, right? Pick if these two are the same, that's du by dx. I can also write the right one if it is the same, it doesn't matter. If that is the case, then this cancels out, and that cancellation is very crucial for the derivative. If you want to define a derivative, that 0 over 0 should not be there. It should be approaching 1, and then the derivative is well defined. So that if and only if condition, it's not if and only if that if condition, you have to capture that, and we want to understand what that means. So if you have so I'm going to define an analytic function now. That is a complex number, that is a function, any function of the complex complex variable. Then I'll define if, so if, right, if you have these conditions satisfied, if these two have to be satisfied, notice the real has to be 0. These are two complex numbers now, right? So if two complex numbers are the same, real has to be the same, imaginary has to be the same. So this will be if du by dx is equal to dv by dy, and du by dy is equal to minus of dv by dx, then that cancellation happens, and the derivative of f with respect to z. Now what is the derivative of the function with respect to z? That's equal to this, but I can write that as, so that's du by dx plus I dv by dx, but that's the same as df by dx. Correct? That's also equal to, I could have, instead of writing this, I could have written that. Right? That's equal, so why not? So write it in that form. So it is dv by dy minus I dv by dy. Write that as 1 over I. No, what am I missing? There's a u, right? That's u. So it's u. So that's the same as 1 over I d by dy, right? So I made this 1 over I put an I and I here, so that's the same as f again, right? This, if you think of it from the directional derivative, this is equivalent to saying that you're coming from the x direction. This is I times y. It is equivalent to saying for coming from the y direction. In fact, it doesn't matter in what direction you come from, these two are going to anyway cancel out. So it is directionally independent. It doesn't matter in what direction you come from. Always this will be the case, and either you can take it with, so since it is directional independent, easiest is to, whenever you have a z, take the derivative with x. That gives you the answer, right? Or remember, derivative with respect to x is the same as derivative with respect to y. In the beginning I emphasized that if it is a plus b, then either the coefficients come in. So if you're taking the derivative with y, then you have to make sure that you divide that by I. If it was minus, then it will be minus I, and so on. So derivative of a complex function is pretty much the derivative with the real point, or if it is an imaginary line, it is I times y. That is as far as operation goes, but it's not the operation that we are mostly interested in. We are really interested in the property, how these functions look like around, like what kind of functions satisfy this, and we want to learn those, what are the properties of this analytic function. That's it. Definition. Let's see what else can we learn out of this. Yeah, so we have, so that's a definition now. So let's think of a function, complex function, which can be thought of as two scalar functions in on a two-dimensional plane, right? On an xy plane, think of two functions, u and v. The function is built out of that. U and v, it is not any arbitrary two functions. They have to satisfy this. These conditions, by the way, are called Cauchy or Cauchy-Riemann conditions. So whenever you want to test that, whether a function is analytic or not, first thing you have to do is this, whether these conditions are satisfied or not. If these conditions are not satisfied, then it doesn't work. Maybe examples are good at this stage, right? So I need to do more. Yeah, first let's do some examples. Simplest will be f is equal to, let's say, z squared. Okay. Z will be just x plus I by itself, so that's too simple. One of the simplest would be f is equal to z squared. What is u and v in this case? This will be x plus iy, the whole square. That's the same as x squared minus y squared. When I square it, it's x squared minus y squared, and then 2 times I xy. What is my u in this case? U of xy would be equal to x squared minus y squared, and v of xy is equal to 2 times x times y. Find all the first derivatives. Du by dx is equal to 2 times x, correct? Du by dy is minus 2 times y. dv by dx is 2 times y, and dv by dy, that's equal to 2 times x. This is the, like, these all first derivatives together are called the Jacobian. When you write it in a denominator, I think Kane pointed it out in the early part of the class, so that's what is showing up. Probably that has some relevance in the discussion that I brought up, but I don't know immediately what it is. But we want to see whether it is analytic or not. If it is analytic, these two have to match. That means when you write it in this form, these two have to match. Yes, indeed, they are the same, right? And these have to match with a negative sign. 2y, they match with the negative sign. When you write it like that, right? That's how you check whether it is analytic or not. At least that's a requirement on analytic. I should point out that you can have this satisfied and still not have it analytic. But if it is analytic, you surely have to satisfy this. This is a necessary condition, but not a sufficient condition. That's the way you would say. Okay. Let's see a function that is not analytic. A nice quantity on a complex plane is a distance between two complex numbers, right? What's the distance between two complex numbers? Or let's say, what's the distance of this point z from the origin? Let's say this is z from the origin. What's the distance between them? What's this length?
Square
Square root of x squared plus y squared, which can be written as z times z star. And then you take a square root, I suppose. Let's make it square of this. Let's say this is the function is the square of the distance, just to make it easier. If I take a square root, then I have to do more work when I'm taking the derivatives, okay? That's a complex function, f of z. If you, I have not written this as a function of z, notice, but there is a specific reason for that. I'll emphasize that in a minute, but let's check what this is equal to. So this is equal to f is equal to x squared plus y squared, and that's it, right? Plus I times 0. So it's clearly not satisfied because this is x squared plus y squared. V is equal to 0, so you would say doesn't get satisfied because this is 2 times x. U by y is equal to 2 times y. This is 0. So the minimal requirement is not satisfied, so this is not analytic. You could have, anytime you see a z star in the function, that's not analytic. It cannot be analytic. Right away you can say that that's a generic result that you get. But why is that? Let's say f of z, notice typically on a complex plane x and y, let me not write this dependence because that gives it away. In general, any function could be f of x comma y, right? There should be two variables. If you're defining a function on a plane, there should be two variables, and that should be x and y. You can write it in terms of z, so now you have a linear combination of x and y as z, but that's just one variable. So I need to have a second variable if I want to be able to write everything on a complex plane. The second variable could be z star. I can have many other variables, z minus iy, right? That could be the other possibility. So if you want to write f of x, y, you would say this is equal to some other function f, which is a function of z and z star. Or this could be a function of x plus iy like this, explicitly, x minus iy. So I can always rewrite any two parameter function in terms of another two variables, and this could be the variables I choose. An analytic function are those functions which does not depend on this. And why is that? Why do I put it like that? Let me say if I have a function of z and z star, so let's go back, right? So instead of prime and other things, let's say in general, the most general function I can write on a complex plane is z comma z star. That's the argument I have made, that if it is two variables, I can choose those two variables to be f of z and z star. And my Cauchy-Riemann conditions is what allows me to make it analytic. So let's see if there is no z star, that implies the Cauchy-Riemann condition. So this is the same as f of x plus iy comma x minus iy, right? So that's what it is, right? Let's see what is the derivative with respect to z star. So partial derivative of f with respect to, maybe first let's do z, right? Partial derivative of f with respect to z is equal to, I have to take, help me, but I want to convert them into x and y, right? Because it is in Cauchy-Riemann conditions. Take the chain rule. This will be z can depend on x. So this is d by dx of dz and df by dx plus dy by dz f by dy. Z can depend on x and y, so I do a chain rule. What is x? Derivative of x with respect to z. For that I have to solve it. So solve this in terms of z and y. X would be equal to, add them out, z plus z star, that is z plus z star divided by 2, and y would be z minus z star divided by 2 times I. What is derivative of x with respect to z? That's 1 over 2. So that's 1 over 2 partial derivative of f with respect to z, right? Derivative of x with respect to z, maybe write that down again. X by dz is equal to 1 by 2 dx by dz star is equal to 1 by 2, coming from here, dy by dz is 1 over 2i, and dy over dz star is minus 1 over 2i, just coming from this point. Using that, I can explicitly write these things. dy by dz is here, so it's plus 1 over 2i times partial derivative of z with respect to z, if you want. Is this what I want? No, there's something wrong here, right? What's it? Oh, x. Yeah. Sorry for that. This is x, so that's y. Okay. Do the same thing with partial derivative of f with respect to z star, which I am proposing that whenever you see a z star, it cannot be analytic. So I would, if I set it to 0, my claim is that it will tell me what these conditions are. That's another way of showing that, but let's see how this works. X by dz star and partial derivative of f with respect to x plus partial derivative of y with respect to z star. And that is equal to x over partial derivative of x with z star is 1 by 2. And partial derivative of y with z star is minus 1 by 2i. Let's see what it implies to say that this is equal to 0, because my claim is that this will show up in that. So let's write it here. So if partial derivative of f with respect to z star is equal to 0, that means it does not depend on z star, right? That's what it means. If a derivative is 0, that means that variable doesn't exist. That means this has to be 0. 1 by 2. This is 1 by 2 partial derivative with respect to x minus 1 by 2i. Respect to y is 0. So let me write the 0 on the left hand side so that I have some space and keep doing this. F is u plus iv. So it is 1 by 2 can go away. So 1 by 2 du by dx plus 1 by 2 I dv by dx. I'm substituting f is equal to u plus iv, and here I have minus 1 by 2i du by dy, and as I cancels out, it is minus 1 by 2 dv by dy. That whole thing has to be 0. If the whole thing is 0, the real and imaginary part has to cancel out, but let me collect them together, the real and imaginary. So that's this plus this. So this is 1 by 2 times du by dx minus of dv by dy. And the imaginary part is du by dy, or let me write it. This is dv by dx, and since I is in the denominator, I have to take it upstairs, so this becomes plus du by dy. If this has to be equal to 0, again I learn, so this has to be equal to 0, and this has to be equal to 0. So du by dx, it is exactly the same, and du by dy, that's I'm writing the second term first, by dx. So exactly the Cauchy man continue. Whatever I did here, the main content is that for an analytic function, maybe take this as a statement, for an analytic function, partial derivative of z star with f is equal to 0. Better implies there is no z star dependence. It has only z in it. That's the key thing. I proved it for you, but those are the details. It is quite straightforward to remember that f of z, and that's why we always write f of z, right? You should have asked right in the beginning that this is a complex function, they should have two variables. Why is it having only one variable? That's because eventually you do everything, and it turns out that if you want to define a derivative, you cannot have z star in it, and that's why you do that. Any questions on that? If you want to be able to define a derivative on a complex plane, either you satisfy this, not very intuitive, right? Or you say it has to satisfy this. This is not also, neither is this very intuitive when you think of a geometric function on top of it, but these are the conditions it has to satisfy. We will think of more intuition associated with that. If you're familiar with electrostatics, think of electrostatics in 2 dimensions. What is the best way to think of electrostatics in 2 dimensions?
Maybe like coordinate, right? Or what do you mean?
A charge is a point is a quantity in 3 dimensions. It can move around. If I want one of the coordinate to be not active in the sense that there is no dependence on that at all, one of the ways is that you stretch that charge all the way in the z direction, and you talk about all line charges, right? If the whole world had, all of us were tall enough that we go from minus infinity to plus infinity, we are all tall enough and we are all going parallel to each other, z direction practically doesn't exist for us, right? Because everything is the same, because we have all the information in there, and we are also saying that it is symmetric and all that. So in that sense, you have killed one dimension, or there is nothing interesting happening in the z direction. Everything is happening along the plane. Is that clear in the spirit that I talked about? And maybe the question that one should ask is, so yeah, so a point charge, is this readable?
Yeah.
Not much choice, I guess, maybe. For a point charge, what is the Coulomb's law, maybe? Electric field, let's say.
Yeah.
Electric potential, better. Electric potential? Is that clear what I mean by electric potential? Yeah. How much is it for a point charge?
Minus.
Yeah. It's minus the gradient of the electric.
Gradient.
Oh no, I'm saying there is a point charge. What is the electric potential at an observation point R? What is the formula for that? Q over R, right? So you would say this is 1 over 4 pi epsilon naught, right? And this is, let me say this is Q over that, and this is 1 over R, right? Electric field associated with that is the negative gradient of this potential. What is that equal to?
Equals minus q over 4 pi epsilon naught r hat over r squared.
Correct. 1 over r squared, and then there is an r hat, right? And here r squared is x squared plus y squared plus z squared. I'm keeping it at the origin, right? So this is r is x squared plus y squared plus z squared, and r hat is the direction from the center to that. This is for point charge. What about line charge? Line is an extension of a point. I smear the charge on the point and pull it in the z direction. Line charge in the z direction. What is the electric potential? What? How about electric field? That's easier.
It's R minus R dash square. R minus R dash square, that's distance.
We're still talking about like you smeared the charge infinitely or just in general?
Just a line, okay, so don't smear it, there's just a line charge, right? This is really infinitely thin, so it's positively charged, goes all the way to infinity. What is the electric field at that point? one thing you can argue is that this will cancel away, so it will always be pointing outward. That you can argue right away. But what is the formula? Like, how does it depend on?
Whatever voltage that applied and then distance, we need to have that one.
Lambda by
Yeah, good. Very good.
lambda by J,
J.
R or J.
R, right? Good. So what is lambda? But anyway, this is 1 over R. Okay, the main point is that it is 1 over R. If you want, let me write it as R hat. And there is a factor of 2 also comes in. What is lambda here? It is charge per unit length. There is no point in talking about charge because it's infinite. If it is infinitely long wire, there is too much charge there. You cannot talk about a charge. Length is also infinite, but charge per unit length is a well-defined quantity, so it's a density that comes. Notice power got reduced in one direction. R square became 1 over R. What is the potential for that? You have to, it is an integral of this. What is the integral of 1 over R? Natural log R. So this will become 2 times lambda over 4 pi epsilon naught times natural log of R. Next is, so this is equivalent to 3 dimensions. This is practically 2 dimensions. If imagine, like, if there are all angles possible, then it is no more. But if only quantities in this world are line charges, imagine there's a lot of line charges, then there is no z direction. Everything is the same in the z direction. There is no z dependence in the problem. Right? In that sense, it is a 2-dimensional problem. If you go further down, these are planes, right? Plane charge or plates, planar charge, what do we call that? What is the electric potential? And what is the electric field? What is the electric field due to a plate? What is the gravitational field if Earth was flat? Flat Earth? No?
Zero.
No? Zero? What is, for our purposes, Earth is practically flat. What do we see as acceleration due to gravity? Many people will tell you that Earth is flat, and it is very hard to convince them the other way. Why is that? Because Earth is practically flat for us to 2 significant digits. Unless you make an experiment more than 1 in 100 accurate, you cannot prove that Earth is not flat. So acceleration due to gravity being constant, which is 9.8 for us, which goes all the way to 100 kilometers, right? Even in an aeroplane that works. That is a consequence of the fact that it is flat, very flat in our region. Unless you go very far, it doesn't work. So if our Earth was flat, electric field or gravitational field will be uniform. This will be uniform. Right? Inside a capacitor, electric field is constant. Right? Whenever you do an experiment, if you were to have 2 metal plates, connect a positive and a negative charge, electric field is constant. You can go as close as you want to one of the plates, and this will be constant. But what is that equal to? So this is 1 over 4 pi epsilon naught. This time, that is sigma, charge per unit area for a plate. There is no point in talking about a charge, it's charge per unit area. And this comes out to be 4 pi over, there is nothing, right? There is 1. There is nothing there, there is no R dependence, it's a constant. 4 pi cancels out, it is sigma over epsilon naught that survives, right? And this is n hat if you want. Let's tell again R hat, but this is perpendicular, right? So this is sigma over epsilon naught R hat. That's how you will know it as a. So charge alone decides, charge per unit area alone decides that. That's a constant. What will be the phi for this? Or the integral of a constant?
So sigma epsilon naught R.
R, let's say. So this is sigma epsilon naught times R, which is the distance from. We want to go here. This is the line charge. If I'm in a complex plane that's 2 dimensions, I want to think in terms of this. Okay? So I have a phi here. Let me think of a complex function f of z to be equal to, I'll forget about the 2 lambda over 4 pi epsilon naught because that's just a constant, correct? I'm interested, now I'm in complex function that is there if I want to connect with the electric and magnetic field, but now this is log of z. So here there is r, and instead of r I just made it z. I just replaced it with z. It is not, because r is a distance, z is not a distance. Z is really a more like a vector than a distance. It has x plus iy in it. So this is log of x plus iy in it. And I want to ask, is this an analytic function or not? Is this an analytic function or not? So I have to investigate this properties, right? But this is now inside x plus. I have to take out my u and v. What is u and v in this case? Right, I have to separate this into u plus iv, right? So I will write this as u of xy plus I times v of xy. What is u, what is v in this? It's not log of x and log of y, right? Log doesn't distribute like that. Right? How do I do that? Remember, every complex number can be also written as r times e raised to I theta. Remember this last lecture? Right? I can write every complex number this way, where r is equal to x square plus y square, and theta is equal to tan inverse of y over x. This has a nice feature that I can now expand log. Log of a product is distributes itself. This is log of r plus log of e raised to I theta. That's the same as log of r plus I, log and exponential cancel out, times I of theta. So my u is, u is equal to log of r, which is log of x square plus y square, and v is equal to theta, which is equal to tan inverse of y over x. Okay. I will leave it as a quiz for you to show that, because I should have a quiz today, right? To show that this is indeed analytic. Like, show that du by dx is equal to dv by dy, and du by dy is equal to minus dv by dx. Okay, is that clear? So it will come out that this is really analytic. So this is an analytic function. But here I want to concentrate on what is the meaning of this u and v. Like, is there a meaning I can associate with that? So let's go and so let's we talked about a function f which was z square, right? F of z, an analytic function which was z square, or make it 1 over z square, sorry. Yeah, 1 over. Okay. Let's do both z square. This is equal to x square minus y square. We did this in a few minutes back. I times 2 times xy. So u of x comma y is x square minus y square, and v of x comma y is equal to 2 times xy. Pretend that this is an electric potential I will have an electric field electric potential in 2 dimensions now, right? So there is some line charge distribution which gives me this, and I ask what is the electric field associated with that, right? So electric field associated with this would be equal to negative gradient of u, that's equal to minus I hat, right, times 2 times x, and minus j hat 2 times y, right? I switched, notice I started with a complex function. At this stage I switched to doing gradient, and I'm pretending that I'm doing electrostatics in 2 dimensions. Right? That's your electric field. What is the gradient of an electric field?
Gradient or divergence?
Sorry, I meant divergence. Yeah, I wrote the gradient operator. Yeah, divergence of an electric field. Sorry for that. Very good. That's rho by,
Rho x.
not r. Epsilon. Yes, right. That's Maxwell equation. Right. This is the charge density over epsilon naught. So I can say what is that equal to, right? So I can evaluate. I'll dot it with E is equal to I made a mistake, right?
Minus 2 I hat minus.
No, I made a mistake, correct? Because this should be plus, right? Because of the minus sign here, right? So that's
Zero.
plus 2y, right? So divergence is minus 2, correct? And plus 2, that's equal to 0. That's not a coincidence. That's not just because this is this, but any analytic function, this will be coming out to 0. Okay? So that's one, you can say, configuration of charges in 2 dimensions. These are the configuration of charges: electric potential, electric field. This is how it works, right? This is another configuration, but a very dual configuration in the sense that these are the real and imaginary parts of a complex function, right? So this again you do. Let me call this EU, and let me call this EV, right? Electric field, you do another set of charges if you want. That's equal to minus
Minus I hat 2y minus j hat 2x.
2y and minus j hat 2x, right? And again, what is divergence of EV this time?
2y minus, or minus 2y minus 2x.
No, because this is derivative with respect to y, right?
Oh,
This
zero.
is, yeah, this is 0 because derivative, so minus 2 times derivative of y with respect to x, correct? That's 0. And minus 2 of derivative of x with respect to y, this is 0. So different reasons why that goes to 0, but that's also 0. Another thing you notice, so this is the same as saying Laplacian of u, right? Or negative Laplacian of u. And this is the same as negative Laplacian of v, right? The second derivative or 2 gradients put together is called the Laplacian. I'll take one more minute, and that is there are 2 electric fields now, right? Let's do EU dotted with EV. There are 2 different electric field configurations that came in. What is EV dotted with? That this is a minus and a minus, so that's 4 xy. It's minus 4 xy. That's equal to 0. That means this is 0, that is orthogonal at every point in space. So if I were to plot this equipotential surfaces for this, always u and v, so if this was u, right, this was u and this was v, they will be orthogonal at every point. U surfaces and v surfaces are always orthogonal. These are called conjugate functions. So the point is that analytic function satisfy Cauchy-Riemann conditions, but they are not very insightful because they are algebraic. It is never obvious what they mean. But geometrically speaking, you think of them as electrostatics if you want to, or as equal surfaces. These are surfaces which will always intersect perpendicularly. U and V always, for any analytic function, will intersect at a perpendicular direction, and their normal directions will be 0. That's all. I'll stop here. Christian?
Yeah, so this property doesn't only have to depend like on electric field. You could use this like for any kind of
I mean, this is one way of intuition, but if you don't know electrostatics, there will be equal surfaces for this, equal surfaces for this. They will always be orthogonal.
so for
That's a more mathematical statement.
any, okay.
But if you're aware of electrostatics, it's nice to visualize it that way. So
But for like any function though, if it satisfies these conditions,
Yes.
then it's
any analytic function will satisfy this. So they are very constrained if you want.
oh okay, yeah.
Very constrained.
Cool.
In fact, even things the way it behaves at infinity has to be very unique, and I'll talk about that next time. There is no, the infinity, the whole surface is one point. That's not obvious what I mean there.
No.
Yeah, so we'll talk about that.